estimate the land surface temperature, and land surface temperature from the satellite imagery of Landsat 8 satellite imagery, and we will use the B4, B5 and B10, these band images. So what I have done, I have mostly used here this methodology, that we take the Landsat data, then from the band 10 we try to calculate the top of atmospheric spectral irradiance, and then we convert that into brightness temperature at the sensor, and after that we will calculate from the band 4 and band 5, we will calculate the normalized difference vegetation index, and then we will calculate the proportion of vegetation, that is PV, and determination of ground emissivity, that will be eta. From that emissivity and the temperature value, we will use the equation of surface temperature, that is LST, and this document I have followed here, that is created by Rizki Saputra, and it is the from the medium blog, mapping land surface temperature LST using Landsat 8 imagery in ArcMap, but I will be using QGIS. So in this case, I have previously downloaded the data. Now I will download. Now I will see from the month of June. These are our downloaded data. You can see I have downloaded this, and this is the shapefile of Dhanbad, so that I can compare my region of interest from this. Now what I will do, I have to create a QGIS file. Here I am creating a QGIS file. Yeah. Let me name this as a new project and save as. Not in previously I have done the April data. I will show it later. Uh, Now I am doing for June, the month of June. I have done April and May. So LST Dhanbad June. Okay. So now here I will simply take all the files. All the files means only the necessary files. That is for June. I need B3, B4, B10, just three for the time being. B4, B5, B10. Not three, four is needed here. So I am doing the drag and drop. So this is the file. Now I will just rename them from this file. These are now as a GOT file. Rename B10, that is the thermal infrared portion. Then we have B4 and B5. B4 and B5, I think it falls in the near infrared range of the spectrum. B4. Next we have B5. Okay. So now the first formula that we will be using here is this one. I have taken it in the notepad. This one. You will see the B10, that B10 will be converted into the TOA spectral radiance. This thing I have mentioned here. The top of atmospheric TOA spectral radiance. So we have two things. One is a multiplicative rescaling factor, and another is the additive rescaling factor, and then we can have a correction factor for band 10. Here the correction factor is not, I think it is not given here. So from the MTL we can simply write this formula. And how we are going to write it? We are going to do this. First we select this raster. Raster is a type of data set that, if you, raster comes from the Latin word rastrum. Hmm. And rastrum means, if we have a surface, say suppose a cake, and it is topped with some cream, if you just scrape the cream, then it becomes a rastrum. So if we have a surface and you are taking information out of that in the same manner like a layer, so it is a raster file. Now I will select the output layer as L. I am using this value, and I have to make the sure that file is being saved in the exact file that I need. So this is my GHI data and all the data, and I am taking data for April. So no, I am taking data for June. So now in June this file has to be saved L. And what is my formula of L? L formula is given as, you can see there are one multiplicative factor and another this factor. Now how I am going to get this? If you notice in the file, when you download the data, you will get a MTL file. This MTL file gives us idea of different coefficients, different correction factors and all that. So if you look at it, there are reflective sample, thermal line, thermal samples, all these things, and the latitude, longitude of region is given here, zenith, azimuth angle. So our value starts here. You see the group radiometric rescaling. Now our value is here. The additive value is 0.1. So we have taken 0.1. And if we see the multiplicative value, that is in case of 10, that is 3.8 into 10 to the power minus 4, which means here I have taken from the previous formula, that is 3.42 into 10 to the power minus 4, but now in our this file we can see the value is like this. So this is how we recalculate it. Now if I keep it OK, then I will get this L value, which is nothing but the top of atmospheric spectral radiance. And how the L value comes? This is our L value. The value is between 12 to 7. If you do some mistake in the calculation, then the value may come negative. But I don't think the value should come negative. So this is the value. And this is the water bodies. You can see this is one lake and this is another lake that we are more interested in. And this band is a deforested land mining area where there has been lot of trees has been cut and mining activity is done, so always this temperature is higher. Now let's focus on our work. Then after doing this spectral radiance value, we will calculate BT, that is atmospheric brightness temperature. Now atmospheric brightness temperature, it also has two band specific thermal conversion constant from the metadata. Let's see K1, K2 what value is given here. You can see K1 value and K2 value are given here. So based on that, our equation, the other value here, this one is our equation. And of course the K1 and K2 value will be different in this case. Let us see. So I am changing the K1 and K2. Normally, if you take a value in the dry months or when there is sufficient sunlight, then these constants remain almost same. These are standard values. But I am taking the value of in the month of June. In the month of June, there are cloud cover and other many other effects, humidity effects, as it is the beginning of monsoon in this region. So these constants are changing by little bit by bit. So now I will calculate, I will do the same thing. I am doing raster calculation and I name an output layer BT. I ensure that it is being saved in our particular location. So where is GHI? This is GHI, and I will be saving this in the June. Where is June? This one is June. So this here the BT, the brightness temperature value is being set. And what is the status of this Q2 and Q1? Let me check. This Q2 and Q1, this one is, sorry, K2 and K1. This one is our 1329. Is it same? No, I think the value might have been changed little. Let me paste and compare. Yes, the value has been changed. The K2 is increased slightly. So I will be using this formula only, this equation. And then for the K1, let's see the value of K1. It is 799.0.284. 799.0.284. Okay, so that is being changed. And this last value, that is 273.15, this is for Kelvin, to convert that data from Kelvin. So now we can just convert it. So the raster has calculated and we have this data. This is our brightness temperature. As you can see, the brightness temperature varies between um 42 to 13. Now in reality you will not get any place where the temperature is 13. It is happening because if you see these all tiles or the raster files, they are shifted by little bit. So in the border area, suppose one is B10 file and another is another file. Because of this shifting, this border area often generates null value or completely black value, which is not the case here. And the black spots, I am not sure what these black spots are. There is a high chance that if there is a cloud cover in this region, then the black spots may arise. And of course, if there is a water body, the temperature is naturally reduced. That is the okay. That is right. Uh, so we will see it later again. And I am taking all these value in the gray pseudo color, gray band region. Later we will convert it into pseudo color. So before we do that, now so far we have calculated only uh, top of atmospheric brightness temperatures, that is BT. Now after that we will calculate this from the near infrared region. We have to calculate NDVI, normalized difference vegetation index. Now that will be calculated as in the same raster calculator. Raster calculator NDVI. We are saving here also. Now, if I will tell you one another thing, that there can be many um, plugins or many scripts that can convert these files in a smarter way. But I am a beginner in this field, so I prefer to use this manual method so that I can understand if something is getting wrong. My knowledge of satellite image processing is also very limited, so this is my only option. Again, I am saving here for June NDVI, and our formula is very simple. Oh no, the formula is we have taken the bands B5, B4, so it is the minus of that divided by the plus of those two. This one is our formula. And this style formula that can change in ArcMap. In ArcGIS, what happens instead of this inverted comma b45 at the rate 1, that will be represented as b5 dot tif because the file format is tif in both the systems. But here they do not consider that. In raster expression, only double you have to mention that name in the double inverted comma. Okay, so now I am doing it ndvi. The beauty of this normalized vegetation index is it always highlights the region where the trees are most less amount. For example, you can see the water bodies have become darker, and the belt, mining belt or the dumping yard, which I told previously, where there has been mass deforestation, that region is also dark. But it is land area, but still it is dark. On the other hand, near the city areas, surprisingly, you can see that the area is little bit light because of there are some trees in this region, and the rest of the areas are gray. It means there can be some trees, there can may not be some trees, like that. And oh, sorry, this dark area, this light area is actually Parasnath Hill. It is on the northwest part of northwest boundary of Dhanbad district, Parasnath Hill, and it is completely covered with trees. It is like a sacred forest, and so it is happening. Okay. Next, we will do the analysis of proportion of vegetation. It is, I think, it is just as the purpose of doing this is like a scaling factor, that it can scale all the values between 0 and 1. Now we will do the proportion of vegetation factor, that is PV, raster calculator PV. June. Okay. Now the expression of PV that I have written here, some for some reason, many times due to problem of brackets, first brackets and all, they cannot catch the maximum and minimum value. So what I am doing, I can see the maximum and minimum value. Here the minimum value is minus 0.082222. So we will write it as NVDI value minus the minimum of NVDI, that is minus of 0.08 and 2222. So we will write it 0.082222. That is the positive value. Here also the same thing, 0.082222, and the positive value here is 0.444833. So what we have, 0.444833. And after we do that, our expression is valid. If there is some problem, if I by mistake add one bracket here, it will show me the expression invalid, and OK button will be disabled. So you have to solve that way. So now we do this, and we get this PV value, that is proportion of vegetative index. Now from this proportion of vegetative index, what we can get, we are not showing this one. So after that we have to do, using this proportion of vegetative index, we can calculate the land surface emissivity. Now I have found that there are two different methods. One method considers the other effects like water vapor, atmospheric correction, angle of all these things. Then they find some logic to estimate the surface emissivity. But here they are using simply equal to a scaling factor. So because this one is easier and simpler method, I am using this. And while choosing the data set, I have considered only the days where cloud cover is very minimum. Uh, so we can use that one. But if we have such a data set where we can see there are many errors or something, some cloud cover, some haze, then I think the other split window algorithm has to be used. This is a mono window algorithm where you are estimating by single value of that. So this is our surface emissivity eta, and we are, no, it is the wrong formula, and we are using it like this. Surface emissivity eta, valid expression. Okay, now we have got a value. Surface emissivity varies here, in this case varies between 0.986 to 0.999. Now after this we have only one thing to do, that is calculation of land surface temperature. The land surface temperature, if you see, here is a log, natural log E, and then some values, that is W. W here comes from the wavelength of emitted irradiance. In this case the value is 10.899, I think. And the BT is the top brightness temperature, and this 14380, this value comes from the Planck's constant and um, velocity of time. I have to look at it theory, and I will be using the formula here. This formula, no, not this formula. They have shown this. This is a very beautifully written block. So that is why I am following it. But some formulas are different. For example, this square thing does not work in QGIS. So you have to put to the power 2. Yeah, this is now our formula. I have to change some small things. So we have to do the raster calculation. Raster calculator. I think it has identified the right file. So I am naming it LST Dhanbad June. LST June. Okay, so I save it, and this is our formula. Here this one is the wavelength for B10. This BT is arc map formula. We have to change it by this. We can do this selection, double click and it will be selected. Similarly, double click and it will be selected, and the emissivity tip, that is eta, that we just calculated, that is eta. Now okay, it is calculating the raster expression for the month of June, and let's see how the temperature is varying. First I will make all the layers invisible, otherwise the exact difference will not be seen. Okay, so in our value, as we can see, the minimum temperature is 13 degree, the maximum temperature is 42. But again I believe that this 13 value, it is happening in some regions that is quite north, and because of this cloud cover, and we are not interested in this. We are interested in this particular region. Now, to make the boundary, I will be taking this Dhanbad KML file to here. You may think why I have not taken this file, this polygon file, KML, keyhole markup language file previously. The thing is, if I take it previously, then the raster calculator will always automatically try to crop this entire tiles or entire raster file into this small region. And if I do this, our information of water body which I need may be lost. Therefore, it is always better to do the analysis separately and add your area of interest or region of interest at the last, at the end. So now let's do it. mm, we have this land surface temperature file, and we need to visualize it. So I have gone to the properties in the symbology portion, which is naturally selected. The render type is called single band gray. We have to change that single band to single band pseudo color, and that value changes here from 13. If I do this, we will get a value like this. Apply. Okay, so this is the thing. But again, here if you see, the lowest temperatures are here, and which is most probably because of the cloud reflectance. So that is not the right value. We are interested in only this region. So as I can see, in this region, the lowest temperature is in the water body. And if I change the scale, again, properties, say if I make it 20, let's see what happens. Then the water bodies are appearing blue. It is just a matter of scaling and the heat map, nothing else. So again here, as I noted that this is the Panchat lake, this is the Maithan lake. The water bodies, because of large water bodies, the temperature is less. The belt, as you can see, this is a deforested mining area, so this has highest temperature. Again in the middle region, we can see there is a higher temperature. This is because this portion has the maximum buildings. I have shown in previous cases from the Google open building data that the buildings are concentrated in this region. And similarly, I intend to do analysis for all the months and see what happens. Another thing, if a region is blue, that does not necessarily mean that it is the water body. What is the example? This is the example. If you see this region at the outer boundary of Dhanbad district, this is actually Parasnath Hill, where I said, in case of, if you see the normal vegetative index, where is my NDVI? In case of NDVI, this is a bright region because here the maximum number of trees or vegetation is present, and here no vegetation is present because these are water bodies, so this is black. But on the other hand, if you take surface temperature, where is my surface temperature? Yeah, this one. We can see this is blue, this is also blue. So it shows us just a simple thing that we all know, that if you want to reduce the temperature in your locality, you have two options. One, you can make large water bodies in the nearby region, or you can have more vegetation, more trees. So these two are solutions.